Yes, so good evening, everyone, and welcome to the presentation of our final project, which was about machine learning-based segmentation of soft tissues from ultrasound images. My name is Nicolas Bernath. I studied business analytics, and I have work experience in insurance.
Hi, my name is Grisch. I have a master's in material science and experience as a researcher in microfabrication.
Hello, I'm Leticia Fernandez Moguel. I'm a chemical engineer with a PhD in process engineering, and I was a scientist at Paul Scherrer Institute. And we are all now data scientists.
So let's assume you have a sports injury. If you want to check what's the problem or if everything is okay, the only place where you can take an ultrasound is in hospitals or with a specialist. And the reason for that is that working with ultrasound images is very challenging. So first of all, it needs a lot of training to be able to take the measurements correctly. And as you can see on the image on the bottom left, without specific know-how, it is very hard or nearly impossible to interpret these images. So for our final project, we partnered with Aison Technologies, which is a Swiss startup which offers a solution for exactly this scenario. And their goal is to, or the aim is to make ultrasound measurements and diagnostics available for non-experts. And to do so, they use innovative technology, which is on the one hand a body scanning system, and the images are then transferred to a software solution which enables in-depth analysis of these ultrasounds. So to enable such analysis, the software has to be able to detect and distinguish different body parts. And that's exactly where we were working on for our final project. So during the last 4 weeks, we worked on building a deep learning model which is able to predict soft tissues such as fat or muscle.
We started our approach with ultrasound images that were provided to us from our partners at Aison Technologies. A medical expert of their team manually labeled them, which you can see here named ground truth. In this case, this image has two separate types of issues indicated. One is fat and one is muscle. Fat is colored red and muscle is colored blue. We then trained neural networks to make predictions of the exact location of fat and muscle tissues on new images, on different ultrasound images. This process is commonly called image segmentation. We made a short animation to visualize how this works. The animation shows the model's prediction on a single image and the corresponding accuracy metrics plotted over time. As you can see in the beginning, the prediction is completely wrong, but eventually the model will learn and find the exact location of fat and muscle, and then from there on gradually improve to even match the borders correctly. We actually tried two different neural networks for this, both were variations of the UNet model, but they performed very similarly. In the end, when the training is completed, the models were able to achieve accuracies of more than 90% for both classes, fat and muscle.
And with these very good results, the natural choice was to create an app, which I'm going to show you right now. We are going to it. The app has a demo mode where we can see predictions of the training history of the data, and we can see results. Here, sorry for that. We can see an example of the fat predictions that are labeled in red. Here is the original ultrasound on the left, and on the right, we can see in white is where the real mask is, and in red is what the prediction made. And we can see how well this area is captured by our model. That is true with the UNet model that is shown here, and by a second model that is called MobileNet. As you can see here, it also predicts very well this area. The app also has an animation. I won't go there because Roman already showed you that. And it has, the coolest part of it is the prediction mode, where you can on the spot load an ultrasound. We are going to show you a calculation for fat and muscle. We just have to go, browse the image, choose one, open it, wait for a couple of seconds, and there you go. On the left, you have the original ultrasound. On the right, you have the prediction. In red, we have the area that corresponds to the fat, and in blue, we have the area that corresponds to the muscle. And this is a very good prediction, and it's similar by the mobile net model or by the UMET model. You only have to change it here. And again, you have in red the fat, in blue the muscle. And with this, we can help non-specialists to identify tissues on ultrasounds with this application. With that, I will go back to our presentation to reach our final conclusions.
Yes, so let us recapitulate the most important points of our project. First of all, we were able to build two models that are able to predict fat and muscle with a very high accuracy. And we were able to create the first prototype of an app which is able to make real-time predictions for new ultrasound images. And last but not least, as an outlook on how this project now could be continued, the good performance really showed us the great potential of these models. So it would now be interesting to add more complexity and try to predict more tissues such as ligaments or nerves, or even go one step further and try to train the model so that it can detect injuries. That's it from our side. Thank you so much for the attention. And if there are some questions, we will gladly answer them now.
Hey guys, it's Mark here. Very cool project. I have quite a few MRI pictures of my knee from a little while ago. I'm wondering if your model, do you think you can use it in a kind of transfer learning way directly on different types of input for the same tissue separations? Or would you need to completely retrain from scratch for this kind of transfer?
I can take it. I don't know, I'm not a medical expert to tell you how similar ultrasound or MRI are, but like telling, I guess they're usually black and white grayscale images, right?
Yes.
And from similar body parts, I would assume that, yeah, transfer learning is possible. We did our model, I think one of them was pre-trained, but obviously it was pre-trained on, I think, ImageNet, so completely different images, which didn't really help much. But if you could train on similar images, I think it would help, yeah.
Cool. Good work, guys.
Thank you, Mark. Thanks for the question. I see a lot of compliments on the chat for your work. I hope that will lead to some more questions.
Yeah, so I'm interested in the other criteria. I mean, you touched on it at the end, but so if I understood right, so far you concentrated on a binary criterion, fat versus muscle. So what do you think are the most exciting other criteria to look at next?
Well, it's also a multi-class problem, especially the second one. We had the muscle and the fat. But of course, there will be other things to add, like ligaments, nerve, etc. Unfortunately, we are not experts to label those. We will require a medical expert to create those masks for us and be able to retrain the model with them.
I would add maybe inflammations and injuries. That would sound really useful to me.
But if you have an injury, you go to the, in order to get the ultrasound, you have to go to the hospital anyway, right? So there you have the experts to interpret the results.
That is true. Not many are trained, and maybe like a family doctor could do the experiment or the diagnostics, because ultrasound is not that expensive, or even a nurse could do it. That was the idea.
Okay. The doctors, the hospitals are going to be very upset at you.
No. The idea is not to replace the doctors, not at all. This is to make the ultrasounds more accessible for simpler problems, for problems that probably doesn't really need a doctor. But one example was athletes that they will need to check how an injury is going in order to train. They are not going to take the time of a doctor all the time they do that. So that's really the idea, is to make it available for simpler cases.
Yeah, I was not being completely serious. Indeed, I think there's great potential.
Thank you. Thank you very much.